Good afternoon, ladies and gentlemen. My name is Ryohei Takitoge. I am from the University of Electro-Communications in Tokyo. Today I will talk about temperature beat, persistent and energy harvesting wireless temperature sensing scheme. This slide shows the outline of my presentation. First, I will introduce the beat sensor concept. This slide shows photo of the beat sensors. We have developed two types of beat sensors. The power beat sensor concept is expanded into a temperature beat sensor. We measure the power consumption of existing electrical equipment by using the power beat sensor. The power beat sensor was presented in IEEE Ishibashi last year in Singapore. Today, I will talk about temperature beat sensor. We have newly developed. This slide shows the concept of beat sensor. Where multi-sensor nodes are distributed, for example, the power sensor is attached a heater or a refrigerator, while the temperature sensor is attached the air, soil, or water. Each sensor node sends preassigned ID code repeatedly to the receiver. The receiver receives RF signals of the beat from many sensor nodes and sends them to a server through a PC, smartphone, or MCU. Application software running on the PC analyzes the repeated signals like heartbeat to recover sensor data by the interval time of the beat ID signals. Sensor data from both the power and temperature beat sensor are recovered by the interval time of beat ID signals like this. Next, I will discuss temperature beat operation. This slide shows the structure of the temperature beat sensor node. The sensor node consists of an MCU, 2.4 GHz RF module, other electronics parts, a thermistor, a lithium-ion secondary battery, and a solar cell. The sensor node has many features, including energy harvesting by a solar cell. Bill of material is less than $30. Size is 50 by 35 by 15 millimeter. This slide shows a block diagram of sensor node. The sensor node consists of these three parts. Power generator is composed of a solar cell, a diode, and a lithium-ion secondary battery. The lithium-ion secondary battery is used to output a fixed 3.7 volt. Beat circuit is composed of a thermistor, a storage capacitor of 1000 microfarad, voltage detector, low drop regulator. The thermistor has temperature characteristics, so it is used as a temperature sensor. ID transmitter is composed of an MCU and RF module. No analog to digital converter is needed in this system, so a simple circuit leads to low cost. This slide shows temperature beat generating waveforms. At 5 degrees C, the storage capacitor is charged. When VST reaches VH, the voltage detector enables the LDO to supply 1.9 volts to the MCU and RF module. The RF module transmits only an ID signal. The VST decreases while the MCU and RF module are in operation. Then VST reaches VR. The voltage detector turns off the LDO. After that, the storage capacitor starts charging again. The interval time Ti corresponds to the resistance of the thermistor. In other words, the temperature is recovered from interval time Ti. So repeated transmission like heartbeats are called temperature beat. The time required to charge becomes shorter at 30 degrees C because the resistance of the thermistor decreases. We can calculate the temperature by using interval times Ti or the temperature bit. VST is integral of current I to charge the storage capacitor. This slide shows the RF module current waveform for single bit. The operation waveform consists of an initialization phase of 4.5 milliampere and 34 milliseconds, and a transmitting ID phase of 15 milliampere and 5 milliseconds. The output voltage of the LDO is 1.9 volt, so that the transmission energy to send ID is 0.43 millijoule, where packet structure is shown here. After transmitting the ID, the RF module keeps operating until the energy in the storage capacitor is lost. So the energy in the storage capacitor is 1.38 millijoule to send single temperature bit. Next, accuracy and resolution. This slide shows accuracy and resolution. Note the relationship between interval time Ti and temperature. The interval time of the temperature bit is 0.6 seconds at 90 degrees C and 66 seconds at minus 21 degrees C. The system covers this temperature range. In the next graph, the horizontal axis indicates difference temperature, and the vertical axis indicates the calculated temperature. This shows the accuracy of the system. The error was within plus minus 0.655 degrees C. Since a time resolution of the receiver system is 10 milliseconds, the resolution of temperature minimum is 0.002 degrees C at minus 21 degrees C, and maximum is 0.694 degrees C at 90 degrees C. Interval time Ti is determined by integration of the current in the storage capacitor, so low noise and high accuracy are obtained. Next, measurement results. This slide shows average power corresponding to various operating temperatures. The power is 0.2 milliwatts at the annual average temperature in Tokyo, which is 16.4 degrees C. This slide shows measurement for the merge sensor node. The photo shows a receiver connected to a PC and two sensor nodes, where ID3 is the temperature near the window, and ID7 is the temperature in the soil over plot. The temperature bits from two sensor nodes were observed at the same time. We observed temperatures for two different locations for 24 hours using this scale. Next, the advantages of the bit sensor. This slide shows power consumption of sensor node. Intermittent operation has some disadvantages. Energy of MCU while the ADC is operating for sensing, and that of the MCU for long sleep times are large. Comparatively large data size increase energy for the TX. When communication fails, data is gone. On the other hand, with regard to the bit sensor, it has low power operation because there is no ADC. The interval time represents the average temperature between two temperature bits, so this scheme does not use intermittent operation, but a persistent sensing scheme. Since noise occurs during the time between the two temperature bits, it can be almost eliminated by averaging of this scheme. Even if communication fails, data can be recovered by this integration formula. This slide shows systems immunity to communication failure. Abnormal data is detected by the PC application software, as shown this slide. Finally, I will conclude my presentation with a summary. In conclusion, the features of the system are listed in this table. The system is persistent and has a low-power wireless temperature sensing scheme using temperature bit. This temperature bit sensor scheme has advantages such as low power, small size, high accuracy, immunity to communication failure, low cost, and persistent sensing. Therefore, the temperature bit sensor is suitable for IoT sensors at trillion sensors universe error. Thank you for attention.